Yeah. Right time.
Okay.
Sure.
Yeah. Hello, everybody. Welcome to the second semester of our Global NCG Seminar, Asia Pacific Node. And today we are happy to have Tristan Bice from the Institute of Mathematics of the Tech Academy of Sciences, who will speak about Dauns-Hofmann-Kumjian-Renault duality for fair bundles and structured system algebras. Okay, let's welcome.
Yep, thank you. Yeah, it's the title is a bit of a mouthful, but thanks for the introduction, and thanks to the organizers for the opportunity to give a talk. So to start with, I thought I would just give you a brief sort of overview of the history of these kinds of duality. So it all begins, of course, with Gelfand. So he had this nice duality in the 40s between commutative C-star algebras and locally compact Hausdorff spaces. So one direction is sort of probably everyone knows, you start with a locally compact Hausdorff space. You look at the continuous complex valued functions on that space, which vanish at infinity. And that gives you a commutative C-star algebra, and Gelfand's key insight was that in fact, these are all commutative C-star algebras up to isomorphism.
And after so I have yet another talk.
And so you get this duality between, well, these kinds of structures at least, but it's more than that. It's also between the appropriate morphisms. So on the algebraic side, you have C-star algebra homomorphisms. On the topological side, you have proper continuous maps. And if you want to actually account for all C-star algebra homomorphisms, not just the unital or approximately unit ones, then you need to deal with these partial maps. And we'll talk a bit more about this later on. So this is, one of the first things you learn in C-star algebra theory, and probably one of the first questions you had was what about non-commutative C-star algebras? So your immediate thought might be, well, what about the Gelfand 9-Mark-Segal representation, right? You represent non-commutative C-star algebras on Hilbert spaces. And this is, of course, a very fundamental, very important theorem, but it's not really a generalization of the classic Gelfand duality. It's not really a duality. I mean, you can have one C-star algebra can have many different representations, and there isn't really necessarily a correspondence between the C-star algebra homomorphisms and, say, the Hilbert spaces that they're represented on, the morphisms between them. So it's not really a duality. But there were some people who did come up with a perfectly valid non-commutative extension of the classic Gelfand duality. So the first people were Dauns and Hofmann, and I think later their student Varela. So what they said is, well, we can look at, on the algebraic side, we can look at non-commutative C-star algebras, as long as we have a distinguished central subalgebra. I mean, you can just take the whole center, but Varela noted that actually it suffices to work with some distinguished central subalgebra.
Sorry, can I say something? I still see the first page of the slides, so I'm not sure if...
Oh, really? Does everyone see my slides, or?
I see only the very first page.
Yes.
I don't know if...
Yeah.
Yes, me too.
You need...
Oh, okay. So hang on.
You just try to, I don't know, to close the viewer and then reopen your file.
Okay, I can try that. So, I mean, it says sharing is paused, but I click resume share and it doesn't seem to do anything. I'll try stop share and then I'll try to share again. Okay, share screen. Okay. Is that working now? Okay.
Yes, it works now. Yeah.
Okay. Good. Yep. Thanks for pointing that out. Okay. So yeah. So as I was saying, you got these dualities and between the classic Gelfand duality, and then you're asking about non-commutative things. So what about non-commutative C-star algebras? Well, on the algebraic side, take your non-commutative C-star algebra with some distinguished central subalgebra. On the topological side, Dauns-Hofmann were dealing with bundles of C-star algebras now over locally compact Hausdorff spaces. So not just the spaces themselves, but these collections of C-star algebras put together nicely. And Dauns and Hofmann, I think they mainly were concerned with the duality between the structures, but Varela came along and showed that you can also make this a true categorical duality. So on the algebraic side, you have C-star algebra homomorphisms, as long as they preserve this distinguished central subalgebra you have here. And on the topological side, again, you're dealing with continuous maps and proper maps, at least, between the base spaces. But but it's continuous maps between the base space and the appropriate fibers combined in an appropriate way. The definition is a little bit technical, but yeah, it's basically a combination of these two kinds of continuous maps. So this is a very nice generalization. It's useful in some circumstances. The only issue is that for some C-star algebras, when the center is trivial, for example, then the bundle will also be trivial. It will just be the C-star algebra you started with over a single point, and that won't tell you very much about the C-star algebra. And a lot of C-star algebra work has been very focused on, say, simple C-star algebras where the center is trivial, and so this Dauns-Hofmann doesn't really tell you much. So the next question is there sort of some better way? And indeed, Kumjian-Renault came up with quite a different kind of duality between, on the one hand, C-star algebras, but this time with Cartan subalgebras, right? And on the topological side, you have now Fell line bundles over not just spaces, but Atal groupoids. And so this was this gives you often a much better way for looking at things like C-star algebras, which often have Cartan subalgebras. I mean, I should point out, I guess, that Kumjian-Renault were probably more phrasing this in terms of twisted groupoids, but these are more or less equivalent to Fell line bundles, right, over Atal groupoids. Okay, so this is great, but there are still a few outstanding questions. So the first question would be, well, can I make the Kumjian-Renault duality a true categorical duality as well? Can I also show that I have some correspondence between appropriate morphisms between the C-star algebras and appropriate morphisms between the bundles? And it would be nice if you could maybe unify these two, sort of similar looking results, right? It'd be nice if you could see them both as special cases of some more general, C-star algebraic Fell bundle duality. This is what I want to show you today, but this is indeed possible. To show you how you might do this, I think it's constructed to go back and just to review the classic Gelfand duality and see how you might be able to modify this in a certain way to get something more amenable to non-commutative generalization. So everyone's probably familiar with this, but let's just quickly go through it. So say we have our locally compact Hausdorff space X, you look at the corresponding C-star algebra of complex valued functions, and the motivating question is really, is it possible to recover the space from the algebra? And indeed it is. First, you note that every point naturally defines a maximal closed ideal. So it's just consisting of all those functions which vanish at that particular point. Okay, or equivalently, all those functions for which X is not within the spot of that function. So that's not too hard to observe. The slightly less trivial observation is that, in fact, this accounts for all maximal closed ideals of A. Right? So for every maximal closed ideal, there is a unique point of your space X for which it's exactly this maximal closed ideal. So you get a bijection, and it's more than just a bijection. It really is a homeomorphism when you give the ideals their natural Hull kernel topology. So indeed, this shows you that maximal closed ideals recover the space from the algebra. And once you realize that, well, then you can move on to the sort of more abstract counterpart, where you start with some abstract commutative C-star algebra, and you want to define your space now. So you can again look at the maximal closed ideals, and this time you just have to prove that it's locally compact and Hausdorff in its Hull kernel topology, and that then to get your actual representation, well, you'd simply map each maximal closed ideal to the corresponding element of the quotient. Because the I is a maximal closed ideal, the quotient has to be isomorphic to just the complex numbers. So this is essentially a complex valued function on the maximal ideal space. Right? And the next thing to show is that this map you have defined is indeed a C-star algebra isomorphism onto the entire collection of functions vanishing infinity on the maximal ideal space. And so the upshot being that indeed locally compact Hausdorff spaces are dual to commutative C-star algebras, at least at the object level. Right? We haven't talked about morphisms yet. We'll talk about them soon. But before that, I want to show you that there is a slightly different approach, which is in some sense also classical, but maybe gives us the right point of view to do things in the non-commutative world. So this is really originally due to Milgram. So he said that basically start with a semigroup A. He looked at a slightly different relation, but it's very similar. So I'm going to define this transitive relation I will call domination. So it's perfectly valid in any semigroup A. I say A is dominated by B if I can find some other element of my semigroup, such that SB acts like a kind of unit, kind of like a local unit just for A. So you can check that this is transitive, and in particular, if you look at these kinds of semigroups, just coming from these locally compact Hausdorff spaces, then domination has a very natural topological interpretation. So it turns out A is dominated by B precisely when the support of A is compactly contained in the support of B. So by that, I just mean you can stick a compact set in the middle. Okay, and then we do kind of what we did before. We say, well, okay, is there some sort of special kind of subset which I can define from every single point in my space? And indeed there is. This time, the points correspond to ultrafilters, maximal downwards directed upsets with respect to this domination relation. The ultrafilter this time consists of functions which do not vanish at that point X. Right? It's just a complement of the maximal closed ideal associated to X. And again, this is, I guess, the sort of easy observation. The less trivial observation is to show that every single ultrafilter has to be of this form for some unique point in your space X. And moreover, it's a homeomorphism. The topology now on your ultrafilters is just given like so. So fix some element of your semigroup, or in this case, C-star algebra, and look at all those ultrafilters containing that fixed element A. So that will define a very natural basis for a topology on your ultrafilters. And the one thing to note is that, yes, so this tells you again, you've recovered the space from the algebra, but in fact, you haven't really recovered it from the algebra, you've recovered it just from the semigroup structure. So all this, the addition, the scalar multiplication, the norm, in some sense, this was really just noise, right? Already the product encodes the topological space. And yeah, this is as I said, a classical result of Milgram from the late 40s, but doesn't seem to be quite as well known among operator algebraists, for example. I mean, I only discovered this sort of a couple of years ago, even though I'm pretty sure everyone, learned the classic Gelfand duality as soon as they learned what a C-star algebra was. And so maybe this is sort of the right approach. But before we move on to non-commutative things and try to do something similar there, let's just quickly discuss the functorial aspect of the classic Gelfand duality. So a map between topological spaces is proper, recall, if preimages of compact sets are compact, whereas a map is continuous if preimages of open sets are open. And whenever you have a proper continuous map between two such spaces, then precomposition induces a map in the opposite direction between the corresponding C-star algebras. And it's not just any old continuous, homomorphism, I should say. It's also going to be unital if the spaces are compact. In general, if the spaces are not compact, it will still preserve the approximate units. So it will still be a non-degenerate star homomorphism. And so this is the way I think the functorial aspect is usually stated, that all these approximately unital star homomorphisms have to be of this form for some unique proper continuous map pi. But there is a very simple way of extending things a bit so that you can actually account for arbitrary star homomorphisms. All you have to do is
in the third line, you have one additional pi, yes? There shouldn't be this one pi on the right-hand side in the third line, yes?
Right-hand side on the third line.
Fourth.
Third line.
Yes, just pi hat of 1 y is 1x.
Yeah. Yes, you're absolutely right. Mm-hmm. Yep, certainly. Yep. Yeah. Sorry.
Okay,
one additional. Yep. Okay. So yeah, the easy way to account for all star homomorphisms is to just simply consider these continuous proper maps, but possibly defined on some open subsets of the space X. So then again, you just, to get your C-star algebra homomorphism, you precompose with pi. The only difference is that for all those points where the function is not defined, well, you just set it to be 0. Right? And yeah, it's I don't know, it's almost trivial observation, but somehow when you look up, Gelfand duality on the internet, on Wikipedia or Math Overflow or whatever, then you'll find pages of discussion, but they all seem to neglect to mention this very simple but important fact that if you really want I think, the best kind of duality, then you should allow for proper maps. I guess people are somehow averse to proper maps, even though these are, I think, exactly what you should be looking at. Okay, whoops. So the upshot of all this is that you really do have a categorical duality between the category of commutative C-star algebras and the category of locally compact Hausdorff spaces. So what about non-commutative C-star algebras? Well, how about we start just really simple and we look at just matrices. So, or let's say finite dimensional C-star algebras, which we all know are just direct sums of matrix algebras, right? Complex matrices with complex entries. So things get a little bit more interesting when you start to look at morphisms between these guys. So when you're defining, UHF algebras, AF algebras, the usual way of defining morphisms is to just take, some small matrix and copy it into a larger matrix X many times along the diagonal. And these kinds of maps can be viewed, again, as coming from functions in the opposite direction, right? Any matrix algebra can be viewed as essentially a function on pairs, right? One pair for each position in the matrix. So from that point of view, this is coming from, again, a partial map now, right? From pairs to pairs, right? Simply given here. So just leaves mn fixed if they're both below 2, takes them down a notch if they're above 3, and leaves them undefined elsewhere. That's where you get the the zeros in the top right corner and the bottom left corner. So that's coming from where the points are undefined. Yeah, so it's all well and good, but in this situation, unlike in the commutative case, I guess there are some restrictions on the kinds of functions that are allowed between the pairs. Right? Like if you want to get a C-star algebra homomorphism, I mean, you could try and copy M2, I guess, into the top right corner of M4, and that would give you a linear map, but it wouldn't give you, it wouldn't preserve the product. It wouldn't give you a C-star algebra homomorphism. So a natural question is, what exactly are the conditions on the functions between the pairs which ensure they actually do define a C-star algebra homomorphism, via precomposition? So to explain exactly what the conditions are, it's helpful, I think, to look at groupoids. So to view these pairs here as not just points in some space, but to view them as actual groupoids. So they form a groupoid in a simple way, just by you look at the pairs. If the inner elements coincide, well, then you say the product is defined and is equal to the outer pair. And you can check this forms a groupoid where the inverse is just found by swapping the elements of the pair. And it's probably not too surprising that one key condition that you should have between these functions is that they should preserve this product structure. So you should be looking at functors between these groupoids. And in this case, a functor is fairly nicely described as a map pi, which is determined by some other map, let's say P, on the individual elements of your pair. And so pi is completely determined by this function P and the domain G, because as I said, we're allowing for partial maps here. So the domain is very important. But the perhaps slightly surprising thing at first is that being a functor is not enough, that this is not enough to guarantee you'll get a C-star algebra homomorphism. You also want the map to be what's sometimes called star bijective. So it's just saying it maps stars to stars. Stars, in a general groupoid, a star is just a collection of arrows with common source or a common range, depending on which kind of stars you're looking at. Stars in this case are just rows and columns, right? So you want this pi to map rows bijectively onto rows and columns bijectively onto columns. In particular, this map I had on the previous page is indeed a star bijective function. So maybe I can go back to this map here, right? And this is essentially why it's so important, especially in the non-commutative case, to deal with partial functions, because there's no way you could map a row of 4 things bijectively onto a row of 2 things. You have to restrict the domain in a nice way so that this indeed does hold. So it's the star bijectivity, it's really the key. And just a little side comment, it's also what guarantees that these functors are special kinds of what's sometimes called the Zakrzewski morphism. So a general Zakrzewski morphism is a relation between 2 groupoids. And yeah, it's not any relation. It has to be sort of functorial in some sense, and it also has to satisfy something like star bijectivity. Star bijectivity ensures that these are indeed Zakrzewski morphisms. Yeah, we won't talk about the general Zakrzewski morphisms because these kinds of functors are enough for us. But it's an important thing to point out. Okay, so we've worked out what the the right conditions on the functions between these pair groupoids are to ensure that you get a C-star algebra homomorphism. But it doesn't, again, just give you any old C-star algebra homomorphism. These C-star algebra homomorphisms are very specific, right? You could get much more general ones by taking an arbitrary unitary matrix and conjugating by that, right? So what is really special about these maps? What else do they preserve? Well, turns out they also preserve what's sometimes called monomial matrices. So a monomial matrix is just one where you have at most one non-zero entry in every row and every column. So if you're looking at this map I had before, well, there's really only two cases to consider. And in both cases, you see that it maps monomial matrices onto monomial matrices. Okay. And this is almost the right restriction, but there are still some other C-star algebra homomorphisms which do preserve the monomial matrices and which don't come from such a nice star bijective function. For example, you can have an automorphism of M2 where you just multiply the top right and bottom left by some some modulus 1 complex number. As long as they're conjugate, then this will indeed induce the C-star algebra automorphism. But this doesn't it doesn't come from a simple precomposition with some function. Right? Okay, but this is basically the end of the story. So if you want to phrase this as a theorem, you would say that every monomial preserving star homomorphism between two matrix algebras has to come from precomposition with some star bijective functor from the underlying pairs, followed by some potentially off-diagonal T multiple. T is just the unit circle in the complex plane. So this is like a baby version of the main theorem that I have for Fell bundles. But I think it's interesting to see, even in the finite dimensional world, it does tell you something not completely obvious. And maybe another thing to point out is that there's a lot of work on groupoid C-star algebras dealing with diagonal preserving maps, in particular diagonal preserving or isomorphisms. And if all you care about are isomorphisms, then that's fine, right? A corollary of this previous result would be, for example, that every diagonal preserving star automorphism on some matrix or algebra has to come from some groupoid isomorphism, the pairs, followed by some off-diagonal T multiple. But the important thing to note is that when you deal with more general star homomorphisms, really diagonal preserving is not enough. You really have to move from focusing on the diagonal to focusing more on the monomial matrix. So I have one just simple example here of another C-star algebra homomorphism from M2 to M4, which you can check. It preserves the diagonal. It even preserves the off-diagonal. Right? And that means it even preserves the expectation onto the diagonal. However, it does not preserve monomial matrices, right? As you can see from this last thing here. And as you can see from the explicit definition, it doesn't come from a simple function or star bijective functor from the underlying pairs. So yeah, diagonal, I think you really need to look further afield than just the diagonal if you want to account for general star homomorphisms. So that deals with the commutative case, the finite dimensional case, but we want to do something more general, right? Life would be boring if these were the only kinds of C-star algebras we care about. So first, the problem really is to just find a nice general framework to unify these two kinds of examples. So you could look at continuous functions to matrix algebras, but you could also look more generally at sections of bundles. Right? So basically, the idea is due to Dauns-Hofmann is to say, well, instead of looking at complex valued functions, you look at C-star algebra valued functions, where you even allow the C-star algebra to vary in a kind of continuous way over the space. And so more precisely, you're looking at sections of bundles of C-star algebras. On the other hand, you could do sort of the other thing and say, well, what if I look at complex valued functions, but now with non-commutative domains? And by that, I mean you replace your space with some étale groupoid. And this goes back to Renault and his thesis on étale groupoid C-star algebras. You could look at, I guess, more general étale groupoids with Haar systems, for example, but we only care about étale groupoids. But we want to do things in a sort of unifying way, so we want to be able to actually unify these two pictures. And here it's best to work in the framework worked out by Kumjian. So he looked at Fell bundles, right? So here you're allowed to, they're again bundles of finite spaces with some extra structure over étale groupoids, at least for us. So I'll just quickly give you the definition, even though it may be a little hard to absorb if you haven't seen it before. But so a Fell bundle is first and foremost just a bundle of Banach spaces, right? But you have this extra structure, so that the total space of the bundle should be a topological star semigroupoid. So it's kind of like a groupoid, except instead of an involution, you just have a more general. Sorry, instead of an inverse, you have a more general involution. And what else? Okay, and so you want it to be compatible with the Banach space structure. So you want the product to be bilinear. You want the involution to be antilinear. And incidentally, just quickly, I haven't lost people, have I? Like everyone can still hear me, and is everyone still there? Okay, yep, good. I see a thumbs up from.
Yes.
So. Okay. So yeah, do you want this? And you also want your base space to have some extra structure. So you want it to be an Étale groupoid, right? And you also want this bundle map row here to be not just an arbitrary continuous open map. You want it to be, well, a functor, but you want it to be slightly stronger. You want it to be what's sometimes in category theory called a star, an iso cofibration. So that means these products have to be the same. Definitely when AB is defined, that's a functor, but even when row A, row B is defined. And last but not least, you want to have the standard properties of the norm, right? You want to have submultiplicativity whenever the product is defined. You want the C star norm condition. You want a star square, if you like, to be positive in the C star algebra fiber, right? In the unit fiber, right? So that's one observation you can make, that all the unit fibers now are actually C star algebra. The other fibers, maybe they're just Banach spaces, but the unit fibers are actually C star algebra. So in particular, if you have a trivial groupoid, with a trivial product, then you're really back just in the Dauns-Hofmann situation of a C star bundle. Just a little bit of terminology. So by line bundle, I just mean a bundle where the fibers are all one-dimensional. And by strongly saturated, I mean that all the fibers contain invertible elements. So Kumjian was primarily concerned with saturated Fell bundles, and this is a slight strengthening of that condition. Okay.
Sorry, so B is a total space, yes? It's
exactly.
not base space. G there's
no, yeah. I was using B for,
yes, and B is from Banach.
Yeah. I was using B for
from
Banach. Exactly, yeah.
Okay.
Yeah, I mean, I did sort of try and there are many different letters that people use for these things, and I wasn't sure what was best. I just thought B for Banach. But yeah, maybe it's confusing because you can think it's the base. Okay.
Okay, it's fine, thank you.
Yep, no problem. Okay, so that's Fell bundles. How do we define the reduced groupoid C star algebra? I'll take your Fell bundle, okay, and then you can define this product by convolution. Right? The only issue is that these sums may not always be well defined because, well, if they're finite, no problem. If they're infinite, then you can still define them as long as the partial sums converge, right? You can view the finite partial sums as a net. So as long as the net converges, well, then we can still define the product. Right? So in particular, the product is defined as long as at least one of A or B has compact support. They don't both have to have compact support. But in this case, as long as one of them has compact support, this will be defined for all G. Then we can define some norms in the usual way. So you've got the supremum norm. You can define an involution, as you would expect. You can use the involution and the supremum norm to define a 2 norm. And again, it's important to realize at this stage, all these things could be infinite valued for some A. And in particular, if A star A is not even defined, well, then let's just agree to say the 2 norm is infinite. And last, we define what you might call the left regular norm, or B norms. So here you're just looking at A as if it's some kind of operator on the finitely supported functions, or finitely supported section. Right? So they're certainly compactly supported. So at least the product is defined. However, the supremum of all these norms, that could again still be infinite. Right? So to fix this problem, we don't like infinite things. So let's just look at all the B bounded, continuous sections of your bundle. All those things for which this left regular norm is indeed finite. it's not a C-star algebra. The product, as we keep saying, is not necessarily defined. However, you can check that it is a Banach space. It is complete. So the simple way then to define the reduced C-star algebra is to just take the closure of the compactly supported continuous section, the closure with respect to this V norm. So we know the product is defined on the compactly supported guys, and it's, you know, with a bit of checking, you can show that even on the closure, the sums still converge. So the product is still defined, and you get a C-star algebra. So personally, I just find this maybe a slightly easier way of doing things rather than the usual way where you take compactly supported guys and represent them as operators on some, you know, collection of Hilbert spaces or a Hilbert module, and then take an abstract completion, simply because it's not clear at first that the elements in the abstract completion can again be represented as continuous sections. Right? I mean, you can after the fact try and do this, but just to avoid those kinds of issues, I prefer to first define a larger Banach space and then just take the closure. So that's a crash course on the reduced C-star algebra. So now I'm just going to move this out of the way. Okay, so now we want to recover the groupoid, or at least, yeah, find the right question. This is maybe not itself completely trivial. So let's say we have our saturated Feld line bundle, and we look at, let's say, the reduced C-star algebra. And the naive question you would ask, just as in the classical commutative case, is whether it's possible to recover the groupoid from the algebra. And the immediate answer is that unfortunately no, that there are some very well-known examples where you have different groupoids, even though they do give rise to the same reduced C-star algebra. So that's a bit too much to hope for. But a lot of the time, particularly when you're dealing with, you know, principal or topologically principal groupoids, you'll find that even when the C-star algebras are the same, their unit spaces are different. And we do at least know that continuous functions on the unit space will distinguish, you know, different unit spaces, thanks to the classic Gelfand duality. So what this suggests is that you should also consider not just the reduced C-star algebra, but its diagonal subalgebra. Right? This commutative, nice commutative subalgebra of the reduced C-star algebra. So maybe a better question at this point is whether we can recover G from the C-star algebra and its diagonal. Right? And the answer is yes, as long as the groupoid is nice enough. So as long as it's principal or even topologically principal or effective. And this is exactly what Kumjian-Renault showed. Okay, but what about other G? What about non-principal, non-topologically principal groupoids? What about even finite groups? Well, here you have a bit of a problem because you know that there are two finite groups of order 4, that they're abelian, and that there's only one C-star algebra of dimension 4. So they must give rise to the same C-star algebra. And the diagonal in this case is still also the same. It's just scalar multiples of the unit. So this shows that, well, it might seem hopeless at first to do things with non-principal groupoids. Incidentally, even though the diagonal is the same, the expectation onto the diagonal, I think, is different, right? The kernel of this expectation is different. So there is some hope, at least, that by using the expectation itself rather than its range, that you could distinguish these kinds of examples. But how exactly you would do this, I'm not so sure. A better idea, I think, is to look at this analog of the monomial matrices, a kind of monomial semigroup, which is defined simply as the elements in the reduced groupoid C-star algebra, such that the support is a slice or a bisection of your groupoid. Okay, so maybe an even better question, which is a bit different from the one Kumjian-Renault were asking, was can you recover the groupoid just from the semigroup structure of this monomial semigroup and its diagonal subsemigroup? So forgetting about all the other, you know, addition and norm, etc., even just from this product structure, could we maybe do what Milgram did in the commutative case and still somehow recover the groupoid? And yeah, it's a bit surprising, right? You wouldn't expect this semigroup to contain more information than the C-star algebra, but it turns out that it does. So how do you do it?
Yep. S and R stands for source and range maps, yes?
This S and R, yes, they stand for the source and range. They're meant to be injective on any slice or bisection.
Okay, thank you.
Okay, so how would we do this? How would we recover the groupoid from just the semigroup structure? Well, we can try and do something sort of similar to what Milgram did. So again, let's start with our saturated fell line bundle. We want to recover the groupoids from this semi-group inclusion. So as we did, as sort of Milgram's approach suggests, then let's also look at a kind of domination relation. So it's like before, in that A is dominated by B precisely when SB and BS are kind of local units for A. But we're going to also use the diagonal. We're going to also require that AS and SA lie within that diagonal. Right? And this is exactly what you need to ensure that domination has the same topological interpretation. That it sort of ensures that the supports of A and S match up nicely, if you like. And that ensures that that A is dominated by B precisely when the support of A is compactly contained in the support of B. Okay, and again, the way to recover the groupoid is to look at the ultra filter. So these form a space with the same kind of topology generated by this basis right here. But they also form a groupoid, and a groupoid which is a tile with respect to this topology. The way to multiply two ultra filters is to just multiply the individual elements. This won't quite be a filter, but that's easy. You just take the upwards closure, so they do generate a filter. And in fact, as long as 0 is not within the product of any of those elements of U and V, then that upwards closure will even be an ultra filter. So this does give you an actual partial operation, at least, on the ultra filter. Okay. As before, as in the commutative case, you note that for every single point in your groupoid, there is a natural ultra filter to consider. It's just this collection of all those functions, right, for which G is in the support of A. So that gives you a nice bijection, and moreover, it is in fact a homonym and even an tile groupoid isomorphism from G onto those ultra filters. Right, so this, this is again showing you that even in this non-commutative world, you can recover the groupoid just from the product structure. So this essentially unifies a lot of other groupoid recovery results. So I haven't mentioned all of them here, but there are results by Kumjian, Excel, Steinberg, Troiger, where they all look at various different kinds of structures you can define from an tile groupoid. So C-star algebras, definitely, Steinberg algebras, inverse semigroups, if your groupoid was ample, LP operator algebras. So there are all these different structures, but they all have a product defined in pretty much the same way. And so once you realize that the product is all you need, then all these results are looking quite similar, right? That really you can get them all from just a single result about these semigroups, which I think is kind of nice. Yeah, this is joint work with Lisa Roloff-Clark, by the way, from last year. Next question: what if you wanted to move beyond line bundles? So you're looking at more general fell bundles. Well, then it's not too hard to do the same thing. You just need to consider one extra sub-semigroup. So what I'll call the central diagonal. So it's like the diagonal, you look at all those functions which are supported on the unit space, but you further require that the values are always just scalar multiples of the unit in that fiber. Because I'm assuming strongly saturated, all the fibers have to have a unit. So this gives you something which is central within the diagonal, not within the whole reduced groupoid C-star algebra, but within the diagonal subalgebra at least. And using that, we can, again, just modify the domination a little bit using Z. So we require that BS and SB lie in Z. And again, this turns out to be exactly what you need to ensure domination corresponds to compact containment. It's not quite yet, it's slightly different here now. We're not just looking at the support of B, but you're looking at really the invertible support of B, if you like, right? The elements on which B takes invertible values. Okay, but that's good enough. That still tells you essentially that the ultra filters can recover the groupoid from just this semigroup structure of these three semigroups, a kind of a semigroup inclusion triple, I guess, if you like. So that's recovering the groupoid, but we want to do better than that. We want to actually get a kind of duality. We want to recover the whole bundle to start with, and also turn it into a duality. So to recover the bundle, not just the base space or the base groupoid, this is when you really do need to start looking at the C-star algebra as well. If you want to recover the additive structure of the fibers, well, then you also need the additive structure of the C-star algebra. It's not so surprising. And it also really helps to, again, have this expectation, the canonical one where you just essentially restrict to the unit space. But if you want to make an actual duality, well, you need to work out what the appropriate structures are, right? I mean, we basically know the topological structures. We're going to be looking at these strongly saturated Bell bundles. On the algebraic side, we have these quadruples now, right, consisting of a C-star algebra, a sub-semigroup, another commutative C-star subalgebra, and this expectation. But there's also going to be some non-trivial properties that these guys satisfy, right? It's the same when you're dealing with the Kumjian-Renault theory, right? You can't just take an arbitrary commutative subalgebra and expect to create some kind of groupoid. You need to look specifically at Cartan subalgebra. And here too, there are some non-trivial algebraic conditions, relations between A, S, Z, and phi, which always happen when they come from these Fell bundles. And the idea is to isolate those properties so that you work out, the right dual category, if you like. So to just mention some of these properties, well, they're all probably quite familiar if you know about Cartan subalgebras. So the first thing to note is that A is generated by S. So it's just closures of sums of elements of S, right? So this is like the S is playing the role of the normalizers, if you like, of the diagonal. However, here we're being a bit more general. S may not actually be all of those normalizers. It may just be some sub-semigroup, but it will normalize the diagonal, and it will even normalize the expectation in the following sense. And that turns out to be important. Another thing to note is that S here is the closure of the compatible sums. So in a sense, S is also generated by its dominated elements. You can think of the dominated elements as more or less the functions with compact support. Right? They could actually be some strict subset, but essentially they're those. Again, compatibility here is just it's an algebraic condition, but somewhat similar to how you would define compatibility in an inverse semigroup. Yeah, I don't want to go into the details there. Another key properties is that this sub-algebra Z here, well, it's commutative, it's also binormal and bistable in the following sense. If you take two elements of S and their product happens to lie in Z, well, then you can stick another element of Z in the middle. It won't be a problem, or you can just apply phi to either one of those elements and the product will still lie within Z. And the last key property to note is that Z is going to be large in the sense that it contains an approximate unit for the larger C-star algebra. So these are all these, I mean, they're not too hard to verify, that these are all these properties which are satisfied by quadruples, specifically coming from these strongly saturated Bell bundles. So this naturally leads you to a notion of what I'd call a structured C-star algebra. So it's a quadruple where you have a C-star algebra, you have a faithful normal expectation, so the range lies within S. I'm not saying it's onto S, just lies within S. That S itself, it's a sub-semigroup, it's closed under the involution, it's closed under scalar products, and it generates A. And it's also itself generated by compatible sums of dominated elements, and Z is a large binomial bisexual central C-star subalgebra of the range of phi. So just repeating the properties that I had on the previous page, right? Just making them into a definition. So the first thing to check is that this really does include the situations that we're trying to unify. So what about in this Dauns-Hofmann-Kumjian situation? So what if you have a C-star algebra A and you look at, let's say, the entire center, just to make things easy. So as long as that center contains an approximate unit for A, right? For example, as long if A is unital, this is not an issue. But in the non-unital case, well, it's not immediately, it doesn't immediately follow that actually this is true. But as long as it is true, if it's not, I don't know, just take the multiplier algebra, that would be fine. That's usually what Dauns-Hofmann are doing. Then you get a structured C-star algebra. So the semigroup in this case is just the entire C-star algebra. The Z is just the entire center. And the expectation is just the identity. So it's a lot of the information here is kind of trivial, but it does at least include this Dauns-Hofmann-Kumjian situation. On the other hand, it also includes the situation considered by Kumjian-Renault. So if you have a Cartan pair, then the way to turn that into a structured C-star algebra in this sense is to look at the normalizers. Right? The normalizers play an important role in the Kumjian-Renault theory, and so it's no surprise that they would also be exactly the right semigroup we need to turn it into a structured C-star algebra. And Z here is just the Cartan, and phi is just the expectation, which by definition exists on the Cartan. That's part of the defining property of a Cartan subalgebra. So great, it includes the two key situations of interest. And as we mentioned on the previous page, these conditions are satisfied whenever you define a structured C-star algebra from a strongly saturated Fell bundles. Okay, so that gives you one direction, if you like. The hard part is to reverse that and say, well, what if I have a C-star algebra which satisfies these properties, these sub-semigroups, etc.? Can I somehow define or construct a Fell bundle on which to represent that structured C-star algebra in this form? So that's what you have to do next. That would tell you that you've isolated really the correct algebraic property. Okay, so let's see how we would do this. So you start off, we've got our abstract structured C-star algebra here. Again, look at the ultrafilters just within the subsemigroup F. So the first thing to prove is that these do indeed form a locally compact Hausdorff-Natal groupoids. The next thing to note is that for every ultrafilter, there's a natural semi-norm you can define from that. Again, using a slightly stronger version of this domination relation. Again, the details are not so important. What is important is that, well, from this semi-norm, by taking an appropriate quotient, right, then you actually end up with a Banach space. So this 0U is a closed subspace. Taking the quotient, you get a Banach space. And so that allows you to then form a bundle. You just take all the individual quotients, right, put them together, apply an appropriate topology and also products, etc., show that you can multiply elements in the appropriate fibers and turn this into actually a Fell bundle, which is strongly saturated. And the next step is to show that you can represent your elements as actual concrete continuous sections of your Fell bundle. So of elements of the reduced C-star algebra associated to that bundle. And it's just like you do before, like with the commutative case. So you just map each ultrafilter to the corresponding elements of the quotient. And the final thing to check is that this does indeed give you a faithful representation of your C-star algebra onto the entire reduced groupoid C-star algebra, or groupoid, I should say, Fell bundle C-star algebra. And such that, moreover, the semigroup and the subalgebra and the expectation get mapped to what they should do. Right? The semigroup gets mapped onto the entire monomial semigroup of that Fell bundle. Z gets mapped onto the entire central diagonal, and phi corresponds exactly to the canonical expectation, where you're just restricting to the unit space. So it really represents the whole structured C-star algebra. So this is, this is the outline, but of course, there's a lot of work to do to prove that this is actually true. This is what the paper is really about. So what this tells you in the end is that indeed structured C-star algebras are precisely those of this form for some strongly saturated Fell bundle growth. So we did isolate the right algebraic properties, and we've shown that we've got a kind of duality, at least at the level of these structures. The next question, of course, is what to do about the morphisms. So the morphisms on the algebraic side of things are probably pretty clear, right? So you want to deal with C-star algebra homomorphisms, but you also want to preserve that extra structure that you have. So you want to preserve this monomial semigroup, this central diagonal, and the expectation. So that's the algebraic side of things. And from that, you want to be able to construct some sort of continuous maps. You want to be able to construct some kind of morphism between the resulting Fell bundles. And the way to do it is so first of all, you want to construct at least one continuous star bijective functor, right, in essentially the reverse direction, just starting from such an algebraic structured morphism. And the way you do it is fairly simple. You, again, just take any ultrafilter lying within S prime, and you just take the pre-image, right? This is not quite a filter, but again, just take the upwards closure, and that will give you an ultrafilter, as long as this pre-image is not empty. Sometimes it will be empty, and so in general, this is only going to be a star bijective functor on some open subgroup weight, right? As long as it's not empty, then it will give you another ultrafilter, so it gives you a nice map, which turns out to be a continuous star bijective functor. Once you've got that continuous star bijective functor, well, that allows you to take a pullback of the bundle, the other bundle, right? So So you take a pullback of the bundle associated to that structured C-star algebra, and then you define another map between the fibers of that pullback to the fibers of the other bundle. So it's a little bit, like I said at the start of it's a little bit technical in the sense that it's not a simple case of taking maps from the base space and maps to the fibers. You first have to take a pullback, and then you're composing these two maps. But this is essentially the same thing that Varela did with C-star bundles. So we're just doing something very similar, but with Fell bundles rather than just C-star bundles. And this essentially gives it to you, right? This is by looking at these kinds of Varela morphisms and these structured morphisms, then you can show that exactly this gives you a categorical duality between structured C-star algebras on the one hand and strongly saturated Fell bundles on the other hand. And that's the punchline. That's the key result. So so thank you for your time.
Thanks a lot for the wonderful talk. Are there any questions or comments from the audience?
Sorry, a very stupid question. If you are given a C-star algebra, can you always find the remaining items in the quadruple so that it becomes a structured?
Yeah, almost. I mean, there is this little issue about whether the center of that algebra will actually contain an approximate unit, right? So it doesn't always hold. And I'm just trying to get back to where did I? Okay, maybe I went past it. Okay, here it is. So yeah, you want the center to be large in this sense of having an approximate unit for the larger C-star algebra. This isn't always true, but if you want to make it true, it's very easy by just replacing A with the multiplier algebra, or its unitization. But I mean, the multiplier algebra gives you a more finer bundle, if you like. So it will tell you more about the C-star algebra.
So let's say if the C-star algebra is unital, then you always have such.
Yeah, if it's unital, that's fine. As long as you just the extra data is simple. The semigroup is the whole algebra. The expectation is just the identity. So yeah, in that case, that's fine. Yeah, I guess the only thing is if you replace A with its multiplier algebra, then you'll be representing elements of the entire algebra, multiplier algebra, I should say, on some bundle. And there's no guarantee that if you look at the smaller subalgebra that you'll still sort of saturate the bundle in some sense. But yeah, if you only care about unital C-star algebras, then yes, you can always find this extra data.
Yes. Do you have any homology K-homology theory for the fair bundles?
K-homology theory? No, I haven't considered that. But yeah, I mean, I would hope that you can do a lot of things with this. That you could try and draw connections between various properties of the groupoid and properties of the C-star algebra, maybe the K theory, etc. Like this would be good to see, right?
Okay, Tristan, there is a question on the chat asking you if you can put the slides on the chat.
Oh,
sure. Or maybe we can, anyway, you can send me the slides so I can put on the website.
Okay, maybe that's better. So yeah.
So I have a question for the previous part about the reconstruction from fair bundles from the certain C-star algebras back to the groupoids structures.
Yep.
So these reconstruction theorems, I believe, are meaningful once we have two different geometrical topological situations which lead to the same analytical objects, to the same C-star algebra, etc. So are there any known examples that this really happens?
Are there known examples where
we have two seemingly different geometrical topological situation to fair bundles, etc., while where we can prove we know by calculation that the corresponding C-star algebras are the same?
Oh, okay. Yeah. I mean, well, I mean, there was the sort of the simple example I gave where you just look at, groups of order 4, right? Like over here, right? So they the groups are definitely different, and the discrete topology, right? Then
Yes.
even though the C strategies are the same, there are more interesting examples. For example, there's this work by Dealey, Putnam, Strong, where they look at basically groupoid models of the Jiangsu algebra. And they show that actually there are actually many different groupoid models, and that they can have unit spaces of almost arbitrary dimension. So even though the C star algebra at the end is still the Jiangsu algebra.
Okay, that means that in these cases we cannot recover from the C star algebra back to the groupoids.
Yeah, not exactly. So I mean, in this case of the Jiangsu algebra, the unit spaces are different. So there you can recover it as long as you take the diagonal subalgebra as the extra data. I mean, that's sort of the game you're playing, that if you don't have enough information from the algebraic structure, well, then you add some more algebraic structure and until you have enough to really distinguish the groupoid.
Okay, thank you.
Yeah.
Do you consider the reduced C algebra case? Do you have the full C algebra case, and have the similar question, and consider the similar question?
Similar questions for what exactly? Sorry.
For similar question for full C algebra, and then you just consider the reduced case.
So
the C star
you
algebra
consider the reduced case of the fair bond, the reduced C algebra, the structure C algebra is a reduced case.
Yeah, so I'm always looking at reduced C star algebras. I mean, the problem with, if you look any further, if you look at, say, the maximal C star algebra associated to a Fell bundle or even just a groupoid, then you don't have this concrete representation anymore. Like you have to take a completion, and the different elements in the completion can essentially, get mapped in a canonical way to the same concrete section. So it's not clear to me how you would, what the representation theorem would even be, right? So that's why we always restrict to the reduced. Does that answer your question?
Yeah, I suppose. Yeah.
So for the reduced case, it do not have some exact sequence for invariant open set and the invariant closed set in the groupoid. For the full case, we have the exact sequence that might be.
I'm not sure about sequences, but I mean, part of the reason I was interested in this is that you would like to be able to, say, take inverse limits of your groupoids or your Fell bundles, right? And then at the end you would like to show that the corresponding direct limit of the C star algebras does correspond to some groupoid, right? Like some Fell bundle. And so you want to do that, you really have to make things functorial, which seem to be lacking in the classical Kumjian-Renault theory. So this would help you do that, I think.
Okay, thanks.
Any other questions?
I have a question. So in this original work of Fell, where the base space is classical, what is the corresponding class of C-star algebras which corresponds to the sections of these bundles? Is there sub-homogeneous algebras or something else?
Well, I mean, I think that Fell was originally looking at bundles over groups, maybe even discrete groups, I think. So yeah, and he wasn't really trying to get any sort of duality. Kumjian came along and said, well, no, you could actually look at bundles over groupoids, and he still called these Fell bundles. But I mean, the original things that Kumjian were looking at are basically these line bundles over principal groupoids, and Renault later extended this to groupoids which are affected or topologically principal, but still line bundles. So I guess the main thing here we're doing is we're looking at more general non-line bundles, and that allows us to basically unify it with the previous work of Dauns and Hofmann, where they're looking at C-star bundles.
So they didn't have a corresponding abstract notions on the side of C-star algebras?
Yeah, their abstract notion was just Cartan pairs, basically. So a C-star algebra together with some Cartan subalgebra. So this is a subalgebra satisfying some of the properties I sort of mentioned, right? But where the semigroup, they do have the semigroup, but they don't. I mean, they don't take it as an explicit part of the structure. They always take the semigroup as the normalizers of the diagonal, and that's fine if you only care about principal or topological, the principal things. But in general, if you take all normalizers, that will give you a semigroup which is too large in a sense. So that's why I think it's better to say I have a semigroup given to me which just satisfies the right properties. It doesn't have to consist of all normalizers. It just has to satisfy those properties.
Okay, thank you.
Okay. Any other questions or comments? Okay. If so, let's thank our speaker again for the wonderful talk. It's really interesting.
Thank you.
Thank you. Okay, I'll stop recording.